Hi everyone, in this video, we're going to dive into a more specialized set of number types, unsigned integers. This is a topic that might be new to some of you, especially if you're coming from a Java background, as unsigned integers don't have direct primitive equivalents in Java. We'll explore why they're useful, how Kotlin handles them, and how to use them in your code, all while writing some examples on screen. Let's start by understanding why unsigned integers are needed. Imagine you're working on tasks that require using the full bit range of an integer to represent only positive values. This is particularly useful in low-level programming scenarios such as manipulating pixels in a bitmap. Pixel values like color components are typically non-negative. Working with bytes in a file. Bytes often represent values from 0 to 255, or any other kind of binary data manipulation. In these situations, you want to store a larger range of positive numbers within the same amount of memory that a regular signed integer uses. For instance, a standard int in Kotlin, which is a 32-bit signed integer, allows you to store numbers from approximately -2 billion to +2 billion. An uint, on the other hand, can represent numbers from 0 up to roughly 4 billion. This effectively shifts the entire range to the positive side, utilizing all available bits for magnitude rather than for indicating positive or negative. Now, let's talk about how Kotlin provides these unsigned types, considering a key detail about the Java Virtual Machine, JVM. Unsigned integer types were introduced in Kotlin 1.3. However, the JVM itself does not specify or natively provide primitives for unsigned numbers. This means Kotlin cannot directly change the JVM's underlying architecture. Instead, Kotlin achieves this functionality by providing its own abstractions on top of the existing signed primitives. It's important to note that, as of Kotlin 1.3, the introduction of these types is still in experimental mode. Kotlin provides 4 built-in unsigned integer types, mirroring their signed counterparts in bit width. ubyte. This stores an 8-bit unsigned integer, with a value range from 0 to 255. ushort. This stores a 16-bit unsigned integer, with a value range from 0 to 65535. uint. This stores a 32-bit unsigned integer, with a value range from 0 to 2 to the power of 32, 1, approximately 4 billion. ulong. This stores a 64-bit unsigned integer, with a value range from 0 to 2 to the power of 64, 1. Let's see how to define these types using literals in your Kotlin code. You can use specific suffixes to indicate an unsigned literal. For uint values, you can use the u suffix, lowercase or uppercase is fine. For ulong values, you can use the ul suffix or ul. You can also use prefixes for different number bases, similar to signed integers. Hexadecimal literals still use the 0x or 0x prefix, followed by the u suffix for unsigned types. Binary literals still use the 0b or 0b prefix, followed by the u suffix for unsigned types. Here's an example of declaring unsigned integer literals. Conversions between signed and unsigned types are possible. Kotlin provides conversion functions, similar to what we saw with basic number types. For example, to convert a uint to an int, you can call touint. Similarly, unsigned types support similar operators to their signed counterparts. Let's look at an example demonstrating conversions and basic operations. Attempting to convert a negative int to uint would be problematic without care, as uint cannot represent negative values. Explicit conversion methods like touint will handle this by wrapping the value or throwing an error if strict conversion is needed. Finally, a word on best practices and considerations. While unsigned integer types are powerful for specific use cases, like bit manipulation or working with APIs that strictly expect non-negative values, If you don't explicitly require the full bit range or guaranteed non-negativity across operations, you are generally better served with regular signed integers, int long. For cases where you simply need to ensure a value is non-negative, but don't need the extended range, it's often more straightforward to use a regular int and then add checks to ensure that a non-negative value was passed to your function. To summarize, Kotlin's unsigned integers provide a robust and type-safe way to handle purely positive numerical data, particularly when working at a low level. While they offer specific advantages, understanding their purpose and the underlying JVM implementation is key to using them effectively. That wraps up our discussion on unsigned integer types in Kotlin. In our next video, we'll dive into Kotlin's next component. So, see you guys in the next lecture.